All right, so the lab we're gonna do today is the general sensation lab. Yeah, I think I'm kind of looking at the schedule, and since we have one day that's purely supposed to be lab review, we can actually use half of that day to do like the hearing lab and then other parts of it to do review. So rather than having a whole bunch of stuff all like slammed on you to do this weekend, I'll give you this one piece to do, which I think is going to be a little more tractable. So the general senses. All right, so this lab and actually all the other ones are going to be about the external senses, the classic ones that you learn about, like vision and taste and smell and hearing and stuff. So when we talk about these external senses, the exteroreceptors, we kind of split them into two categories. There's the general sensation, general senses versus the special senses. General senses, which are the ones we're going to look at today, these are the ones that are just found all over your body. From the tip of your nose to the tip of your toes, right? You can feel touch everywhere. You can have temperature receptors and pressure receptors all over, pain receptors. So this is like touch, pressure, temperature, pain. These are all over your body. They have very simple receptors, usually just very simple receptors. The receptors are usually a single neuron, sometimes with a little bit of connective tissue, sometimes not even. There's a lot of like pain receptors, temperature receptors. Some of the touch receptors are literally little, what we call naked dendritic endings. They just have little specialized channels that'll respond to temperature change or to stretch or something. So the receptors are very simple. They're all over your body. Where in the brain do we have the primary cortex for somatosensory senses?
Post-central gyrus.
Exactly, the post-central gyrus. So this information is coming into the post-central gyrus. Special senses, on the other hand, these are in the head. They have very specialized, complicated receptors. This is like your vision with your eyes, or your hearing and equilibrium with your ears, or your taste and olfaction. Taste is gustation is the official word. Olfaction is smell. Those are just chemoreception, as we mentioned. Like taste is different chemicals in your saliva. Smell is different chemicals floating around in the air that you're sniffing up. So we will look at these in more detail next week. What we're going to look at today is general senses. It'll be nice to kind of give a little more of a hands-on experience of what I was saying about how your experience of the world is limited by your receptors, by what they can detect, by how many receptors you actually have to detect things. So yeah, I think this is a fun lab because it is something that gives you more of a reality check on things you've always been taken for granted. This is also a lab that is better to do in person. And what I'm going to have people do is Actually, I'm going to go over the different sections, but I'm going to have you do it at home, because it's not going to be as cool if you just watch a video of somebody doing this stuff, because they can be acting. It's if you actually experience it yourself and see what's going on, it's way fucking weirder. I mean, way weirder, to see the reality of the limits of your sensory experience. So let's review the idea: sensory transduction.
Do you want us to paste in all the parts, part 1 through 6?
Eventually, but we'll talk about how you put it together. We're going to go over each section, and actually part 6 we're not going to do at all. So we'll talk about them as we get to them. So what is sensory transduction again?
It converts stimulus into electrical signals for the nervous system.
Exactly. So that's what the receptors are doing. In this case, we're going to have receptors like in our skin that can detect deformation, stretch of the skin, and you experience it as stretch. Or deeper deformation would be pressure, or temperature changes would be detected as, temperature, hot or cold. The other term, which I have not talked about yet, but you need to know for today, is adaptation. So this one is cool. This is the basic idea. There is so much information and stimuli landing on us at every moment. You put your shirt on this morning and you felt it on your skin. You probably haven't been thinking about your shirt pressing against your skin. I see people with their hair pulled back or braided or whatever. You probably felt your hair getting pulled back when you pulled it back, but you haven't been thinking about it. Or you put on some glasses and you felt the glasses sit on your nose, but you haven't really been even feeling the glasses on. It's a classic thing. I can't find my glasses. Dude, they're on your face. So this idea that you have receptors and they respond when you initially have something happen, but then they eventually stop responding. So adaptation, you stop responding to a constant stimulus. Right, so some receptor detects something in your environment and you pay attention to it. And then if there's nothing like that, if it's not dangerous, it's not yummy, it's not whatever, you're like, okay, I don't have to think about it now. And you stop responding. If something changes, the receptor wakes up again and you notice, oh, there's a change. And then you can detect to decide, what do I want to do here? But in general, whether it is touch receptors, we're going to see in our lab today, they tend to adapt quite quickly, right? You put your glasses on, or you put your clothes on, you feel them, and then the feeling goes away. But the actual touch on your skin doesn't go away. It's still there. You just don't sense it anymore. Like there's still something touching you. You just don't have a conscious perception of it anymore. Sound even, like sometimes like there's like some hum and you kind of just forget about it. You don't even realize it's there. And it's like, whoa, the heater turned off or the washing machine turned off. I didn't even realize that there was that noise and now it's gone. Smell, we're going to see smell adapts quite dramatically. Like if you're in your own house, in your own room, it probably doesn't smell like anything to you. But if you walk into somebody else's house, it's like, oh, there's that smell. Or even when you walk into your own house for a moment, it has that smell, and then it's like the smell disappears. Even really strong smells will disappear quite fast. So adaptation, this idea And it's not just general senses, it's in all your senses, even in vision. If you like paralyze your eyes and just stare straight ahead, everything grays out. John?
When you're listening to the hum of a heater or something like that, and then you pretty quickly tune it out, you're not conscious of it. If you think about it, I mean, as is the case when you just remind us that there might be a hum of a heater or something like that, then you can kind of latch onto it and find it again. Is it? You were just saying it's actually the case that the sensory input stops.
Well, so it depends. So some of the adaptation is happening at a receptor level, like for touch, it's actually happening at a receptor level. So even if you're trying to find it, you're not really going to find it because the receptor is turned off and you actually have to change the input in some way. But some of this other adaptation is happening more centrally, like in your brain. And so that you can more, I think like what you're talking about there, you can kind of reset that just using your mind rather than going to the receptor itself.
Okay. Yeah, that was my question.
Yeah, and we'll see some of the adaptation gets really trippy. I'll show you some visual stuff next week. That's just, again, if you haven't seen it, it's just weird and cool. You just don't realize how much your brain is just constantly adjusting and adapting because you just take all this stuff for granted. So we're going to see adaptation in the general senses today, though. We'll be looking at it in terms of touch. We'll be having it in terms of temperature, right? Temperature. Like right now, it's like you probably don't really feel temperature. Is it hot or cold? Unless it's particularly warm or cool in your room, it doesn't feel like anything. When you first walk in, it's warmer or cooler than where you were. And then you kind of adapt, and now you don't really feel the temperature anymore. Right? So we're going to see that. What about the other general senses? Are there any general senses that don't tend to adapt? Or any senses that don't adapt?
I would think that some chemoreception doesn't adapt if it's stuff that's really important in maintaining homeostasis.
Or the pain receptors?
Yeah, and pain. I'll say pain. Let's put pain in there. Like your pain receptors in general. Again, if you think about what a pain receptor is doing, which is detecting damage to your body, it's going to make sense that you'd rather it not adapt. So pain receptors tend to not adapt, which makes pain management really tricky. You know, because you can have chronic pain that can get really hard to manage clinically. Hold on. I'm gonna, my stylus just turned off. We have a technical malfunction here. Okay. I'm going to go into this thing where, okay, I can use my finger to draw. It's ridiculous.
Can't adrenaline interact with the pain sensors being able to adapt?
Say that again?
I said, can adrenaline affect the receptor's ability to adapt, the pain receptors?
I'm not exactly sure what you mean by that.
Oh. Well, I just mean like when you're in like an extreme scenario where you may hurt yourself, but you're still able to like run away from the mountain lion, and you don't even realize you're in pain until later.
Right. So that might be like also fear, also just really, you can actually distract yourself from one pain with some other strong enough stimulus. So it's probably something to do with that. But so that is that I don't know otherwise if there's some actual relationship between the adrenergic pathways and the pain pathways. There are the opioid pathways that will, like that kind of runner's high, right? If you've been running and you can actually, after a while, you can start slowing down the transmission of pain pathways going up into your system. Those are the ones that get used to use the opioids like morphine or any of those things. But in general, pain receptors, once they turn on, aren't going to just like, oh, there's pain, let's stop. There are these but there are more central things that can modulate your experience of the pain. Okay, my stylus still doesn't work, but I do have my finger. All right, so there's going to be touch. Let's first talk about touch. Touch is mediated by these really simple receptors. They're called like Meissner corpuscles or some of the main ones. There's also other ones, but let's just use those for now. So let's say this is your finger. You've got all these little receptors in your skin. And those receptors are connected to some neurons that then take that message to your somatosensory cortex. So these things are supposed to be my little touch receptors. But your ability to detect what is touch, what's pushing down on your skin, is going to be determined by your array of touch receptors, right? So if I take a needle and push it here, and I have another needle and I push it here, is there any way for me to know, given how I've drawn the touch receptors, that this is 1 versus 2? There's
No.
no, without having a more kind of dense array of receptors, there's no way that I could know. Like if I put one over here and over here, then it's really easy. It's like, oh, this one's on, this is off, this is off, this is on. So I have this information going to my brain. Pressure, no, yes, right? So the density of the touch receptors under the skin is really going to be important for how fine your touch discrimination is going to be. We have this word acuity. Like, how close can these two things be and you still know it's two things instead of one, right? With vision, it's the same thing. How close can the two dots be and me still know it's 2 dots instead of 1 dot? When we look at like the back of the leg, here's your calf. Oh my God, this is bad. I'm using my finger. You might, instead of having those things really close, they might be really spread out, which in fact, you're probably going to find out they are. And again, they're sending their messages up to the brain ultimately. But if the density of these touch receptors is more spread out, you're going to have even worse ability to tell, is it 1 or 2? So the first part of this lab is just to actually map that out on different parts of your body. You can do it with just like a paper clip or anything. You need usually some kind of wire thing where you can set it up, where you can have some distance here that you can measure. And you're basically, back, let me. It's probably going to make more sense to just hold on. All right. I'm going to take my little thing of, here's a paper clip. Just take a paper clip or anything that's similar to a paper clip, and you can set the distance. And you're going to also need a ruler, because we're going to have to be able to quantify, measure what was the distance between the two tips when they could barely feel two instead of only feel one, right? This is going to be one of these perceptual thresholds again, right? If I have these really far apart, it's like my eyes are closed. I can still say there's definitely two things on my cheek instead of one. When they're very close, spoiler alert, there's no way I could tell you that this is two or one. I just feel one, even though if you put it on your finger, it's obviously two. But if you put it here, it's not obviously two. So this is something you're going to do with somebody who's willing to do this with you. You'll have fun with it, I think. You're basically going to be going on these different body parts, on your finger, on the lip, on the cheek, on the forearm. I think we'll look at the details in a few moments. But you're basically going to adjust them. Usually you start small and then go big until you barely feel, I know it's two instead of one. And then double check. Like I said, the same thing that we saw with the nerve stimulation lab with the false positives, it's the same kind of thing. Give them if they feel two, just go with a single thing there. And sometimes they're gonna, oh no, I feel two, I still feel two. It's like, okay, no, you're making that up. So double check, just because they say I feel two, double check that they really are feeling two. Go with just one and see if they say, oh no, that's only one now. Oh no, that's two, that's one. So really don't just trust that as soon as they say I feel two instead of one, that it actually is what's real. So you're going to get the data for your subject, and record that. Again, this is going to be like part one of your lab. So back to what Ethan was asking in the first place. It probably makes sense here, kind of paste in the instructions for part one and then get your data for part one, since you're doing this on your own time anyway. Just record the data for the body parts for that 2-point discrimination. There will also be a spreadsheet showing data from a larger group of students, so you can then compare your results to the bigger results. Another thing that you're going to do that is very similar but different, and I think also really just wild and weird, is touch localization. Touch localization, you basically, again, you have your subject have their eyes closed, and you're going to touch them someplace on their hand with a pen. So you're going to make a dot. And then they have to take a pen in a different color, and they have to find exactly where to touch them and make a dot. So you're not trying to trick them. They get to feel around there, it's not like they have to it's like they can try to get the exact spot and make their dot. Again, spoiler alert, your ability to detect where things are on your skin is limited by the sensory array of touch receptors. You're not going to be that good at it all the time. So those two dots aren't always going to be the same. In fact, they mostly won't be the same. So you're going to use your ruler again, but this time to measure the distance between where was the actual dot that was placed by the experimenter and where was the dot where the person actually thinks they're getting the exact spot. You'll do that a few times, right? And again, you'll do that on different parts of the body. And then your subject will be covered with little pen spots all over their body, but that'll be kind of fun. So let me share here. All right, so this is just showing, a little model of the skin showing like little touch receptors underneath. Again, 2-point touch discrimination. The caliper you're going to use could just be like a bent paper clip. It just has to be something that can hold its distance with two things that will push. And a ruler, you need to have some ruler that can measure in millimeters so you can detect the distance. I'm assuming everybody has a millimeter ruler at some point in their house. If not, you should probably get one. You're going to look on the face, back of the hand, the palm of the hand, the fingertips, the lips, back of the neck, back of the calf. So you'll just do that on each of those things and see what you see. Record your data. And then again, we'll have the data from the overall class as well. Tactile localization, that's the other one I was telling about, where you have one dot that the experimenter puts on the subject, and then the person has to put a dot where they think is the same. Do it on the palm, on the fingertip. Ventral just means if you're standing in anatomical position from anatomy, it's like the front part of your forearm or the front part of your upper arm and upper back. Where do I have it? Here it is. Let's go back. In this thing that says doing the general sensation lab, if you're confused, you can, look, we have little videos where I just kind of have examples of people doing it so you can see what it looks like.
The body for comparison. Let me know if you feel. Two.
Right. So if you're still confused about exactly how to do it, you can watch these videos. Tactile localization as well. You can watch, she draws on the subject, and then the subject gets a different colored pen and has to show exactly where she thinks she was touched with the original dot. So again, if you're not sure what I've been talking about or how to follow the directions on the written part of the lab, you can watch these little videos that also show how it's done. And again, you're going to do 2-point discrimination as well as tactile localization on the different parts of the body that are listed in your lab manual. Any questions about those parts? Again, this will be something you have to kind of do at home. You have to find somebody who's willing to do this with you, but it's actually kind of fun. So the next parts are about adaptation of touch receptors. For adaptation of touch receptors, you're going to put coins on your arm. And again, you'll have your eyes closed, or not on your arm. You'll put coins on the arm of your subject. I should mention that coin or anything that is kind of cold that pulls away heat, you'll feel the temperature difference rather than the touch. So it's good to use some kind of tape or something like, let me have right, here's a coin. If I put a coin on my arm, it's cold more than it's even pressure. So putting some kind of something insulating on there. So now I don't feel the cold and it's more a touch. And I'm going to have my subject there sitting with their eyes closed and see how long does it take till they just don't feel it anymore. And it'll happen pretty quick. You know, and then you'll add a few more coins on top to increase the pressure. What happens if you change the pressure on the receptors after they've adapted?
They'll feel it again?
And why is that? So again, idea of adaptation, right? If the receptor adapts, you know, it's not responding anymore. If something changes, the receptor is going to wake up and make you aware something's different. And so you can pay attention again and see if there's something you need to deal with. So receptors adapt, but then when the stimulus changes in some way, the receptors wake up again. So which makes sense. Adaptation is good. It stops responding to a constant stimulus, but if the stimulus is no longer constant, if it's changed in some way, that's going to make the receptor start responding again, and you'll notice it. So you're adding more weight. You're changing what the stimulus was. So now you're checking, is this something I need to pay attention to? But then wait a little while and see what happens. And again, when you're doing this thing with the coins, make sure that they're not feeling temperature, because temperature is gonna not adapt as much. So make sure that you've kind of insulated the coins from the skin. There'll also be something in that lab procedure about bending a hair. So just find a hair, and everybody has hair on their skin. You know, some of them are more fine, they're kind of harder to see, but find a hair, just bend it. It could be with a pen or a pencil tip or something. You'll feel it for a moment. So you're going to describe that experience. I should mention like about hair. And we talked about the Meissner corpuscles and stuff. Oh, my pen is working again. Let's see, this is your arm. Yeah, and you got all sorts of little hairs on there. Those hairs, if you remember from anatomy, a hair goes down to the hair follicle. And at the base of the hair follicle, there's this thing called the root hair plexus. Which detects bending of the hair. Your touch receptors, they're pretty like good, but they're not able to detect super light things, right? If you were just using your normal touch receptors and a fly landed on you, there's no way you'd feel it. It doesn't have enough weight to really bend your skin enough. But these hairs act as levers. So when the hairs bend, you feel things. Like if you blow on your arm, you'll feel that wind on your arm. You're not feeling the touch receptors responding to that breeze of your breath. You're feeling the hairs bending in response to the wind. And as those hairs bend with their little lever arms, they're activating that root hair plexus so you can feel that super light. Like if a bug lands on you, you're feeling the bug bending your hairs. So the hairs give you this really fine kind of touch. But you're gonna get to see how fast they adapt, right? Because it would be kind of annoying if you just felt everything on your body all the time. So, but that's going to be part of adaptation of touch receptors. That's going to be part 3. It's just going to be bend a hair and describe it and put some coins on your subject's arm and time it and see how long it takes the feeling to go away. So that's going to be the touch stuff. So touch, we're going to do the 2-point discrimination. We're going to do the touch localization. We're going to do the adaptation. So that's going to be general senses for touch. Again, it'll take you a little while. It's not going to take you that long to do at home. And we're going to go over the temperature and the referred pain thing, but then we're going to end our lab early today so you can actually do this at home, because I know this is taking up time for you to do this. So I would say take advantage of that time to just do it, because assuming you might not have somebody at home to do it with, in which case you'll have to wait. But if you have somebody who's around, maybe you have a kid who's like would rather not be doing their homework or whatever, see if they want to just be a subject for your experiment for like a half an hour, and you can get some data off of them and then just be done with it rather than have it hanging over your head. So that's the touch part. The other things we're going to look at are temperature. So temperature receptors are kind of, they're strange and complicated, where there are cold receptors, they're heat receptors, although they're a little more complex than just that, but they do tend to respond more to like changes, things becoming more warm or more cool, and they tend to adapt quite a bit. So we're going to do a couple of experiments looking at adaptation of temperature receptors in your hand. And to do these, you're going to need bowls of water. So, the first part is you're going to have a bowl of water. You're going to have warm water. So when I say warm, I wrote in the lab manual, like I think what I wrote, 43 degrees. You might not have a Celsius thermometer around. Warm, it means it's very comfortably warm, but not hot. Any of these things, to look for adaptation, we can't be in pain, right? It just has to be, it could be cool, but not too cold where it hurts, or warm, but not so warm or hot that it's uncomfortable. So when I say warm, it should feel warm, like, ooh, that's nice and warm, but it shouldn't feel like, ouch, ooh, this is starting to hurt. I want to pull my hand out because I don't like this. It should be like, yum, this is kind of just nice and pleasant. So you'll start with warm water. For all of these experiments, you need to describe what the experience is of temperature. So you're going to put your hand in here. Start a timer. So when I say this, don't say it feels wet or it's painful or it's tingly. That's not temperature. What I really want to know, is it warm or is it cool? Or what, talk about temperature. Don't talk about the feelings and, other kinds of things. Describe the temperature. So, how does it feel? How does it feel? Is it warm? Warmer than it was a moment ago before you immersed it in the water? And then you're going to wait a couple of minutes and you're going to put your other hand in the same thing. And again, you're going to describe your temperature perception. What does this other hand feel like now? Especially, how does it feel compared to the hand that's already been sitting in that same water for 2 minutes? This hand that's been in the water has had a chance to adapt. From just our discussion, what do you think is going to happen to your perception of the temperature as the hand has been sitting in the same water for 2 minutes?
It won't feel as warm.
It's not going to feel as warm. This other hand that's going directly in, it has not been adapting. It's going in straight. So it's going to be really interesting to be able to compare. What does it feel like to have a hand that's been adapting, and what is its temperature experience of this water versus what's the experience of the hand that has just freshly entered the water? You're going to compare those two experiences, perceptions of temperature in those two hands. This is where it's a little tricky to do with one person. So if you could have a subject again that you are having do this, so you are free to record in your lab book what they are experiencing. It's better to have your subject do this so they can report, and then you can write down what they're saying. Because obviously you're not going to be able to write your own experience in the lab book when both your hands are in a bowl of water. If you are doing it on yourself, you can try to remember, but it's usually better to record things in real time as people are actually experiencing them in the moment. So does this part make sense? The other part that's part of this part 4 that I think is super cool is I'm going to take 3 bowls. So this is going to require a little more of a setup to do this. You're going to have 3 bowls. Again, each one has to be big enough to put a hand in. And the water, again, the water temperature needs to be not painful, but this is going to be cool. This is going to be warm. And this one's going to be kind of lukewarm. Somewhere in between. So before you actually put your hands in and do the experiment, you want to just feel one after another. This should feel cool, but not super cold. Like there's a video I have where they have ice. Don't use ice. Ice is pain. This should just feel like cool. This should feel warm, but not hot. This should be in between. If you put your hand from here to here, this should feel warmer than this and cooler than this.
11 a.m.
If you're going from here to here, this should be cooler than that, but warmer than that. So use your hand to double check. that these three are cool, lukewarm, and warm, but not painful. None of them should be painful. They should always just be kind of cool and warm, somewhere in between. And once you've got that set up, you're good to go. This is something, I mean, I remember doing this as a little kid, and it was just like the weirdest thing. And I think if you've never done this, it's super cool. I think you will enjoy it. You basically take your hand, one hand goes into the cool water, one hand goes into the warm water. And they just sit there for like 2 minutes. And they get to adapt. So you already are going to have a sense of what's going to happen here. They're going to adapt. Then after 2 minutes, you're going to put both hands in the lukewarm water. And I would say also wiggle your fingers around. If you've ever been in a hot tub, you probably realize like there's this kind of insulation that happens right against your skin with the water. Like you move and all of a sudden, I feel more the temperature of the water for real. So you wiggle your fingers around to make sure you're feeling really fresh water against your fingers. Wiggle your fingers, and again, describe the temperature in one hand versus the other hand. And again, remember, both hands are in the exact same water. If you've done this right, you're going to have a very strange experience of very different experiences in hands of feeling the exact same thing. So you want to describe what the sensation of temperature is in your right and left hand. We're going to have this idea of a negative after image. If you've adapted to something that is cool, then what is the lukewarm probably going to feel like?
Hot.
Probably going to feel hotter. And if you've adapted to something like normal is this warm, then this all of a sudden is going to actually feel kind of cooled. This adaptation in this negative after image, it can get weird. Actually, they've shown like if you show people like lots of pictures of really like attractive, people, so how does this work? You just keep looking at pictures of people that are considered classically handsome and beautiful, or you see lots of pictures of people that are homelier looking or whatever, and you can adapt to that even. And then you just look at here's some like random person picture. If you've been watching a bunch of people who are classically super handsome and beautiful, and then look at this person who's kind of just in the middle of it, they're going to look less attractive to you. Whereas if you've been adapting to the kind of more homely faces, and then look at this, they're going to look more attractive when you're rating it. It's kind of bizarre. This kind of adaptation doesn't even just happen on a temperature level. It can happen in these more into like central kind of things. But we're going to see in vision, there's all sorts of, I'll show you some examples of this in the visual system later that are really cool. But for this experiment, you're going to just see it here in terms of something really low level with the temperature. If you are just getting used to things being cool, this same thing is going to feel warmer than it would have otherwise. If you're just used to things being warmer, this is going to feel cooler than it would have been otherwise. So I want you to actually do this and experience it and record your experience or your subjects experience in your lab notebook. So if we kind of go back here, again, adaptation of temperature receptors. You know, it says, do not use ice water. The video uses ice water. That's not what you should use. Please don't. It's going to be pain. In fact, we're going to use ice water in lab when we do the cold pressor test. So don't use ice water. It's painful. If we go back to the let's see. PDF. Let's go to the PDF here. Again, you can follow this. You know, cold but tolerable, not painful water. If you feel pain, the water is too cold. I write this. I can't tell you how many times we do this experiment and I read people's reports and it's like, so what is the experience of being in the cold water? It's painful. It's like, then you should have made it warmer, right? So please, if it's painful, then it's too cold. Don't just write down, oh, it's painful. It's like, adjust the temperature so it's not that cold. So referred pain. One of the things that we normally do if we were in person, but I'm not going to have you do at home, is to do referred pain. Let me talk about referred pain a little bit. So the basic idea with referred pain is that while you do have pain receptors for your internal organs and structures, they are not so good at localizing. Like, you know, if I have pain on my tip of my nose, I can say, ooh, the tip of my nose is in pain, or ooh, I got some major pain in my index finger, but if you have pain on your kidney or your heart or something like that, it's like there's something wrong, but it's hard to know exactly what is in pain. But there is this interesting thing that helps you kind of understand what's going on. And referred pain is when you get this crosstalk between pain receptors and like your organs, your deeper structures, that ends up feeling like it's coming from more surface pain receptors. So like a classic example is a heart attack. If you're having a heart attack, often you feel like you have pain in your left arm, even though your arm doesn't experience any pain. So like, let me draw, here's a picture of a person. Oh no, I have a heart attack. Give him a brain. So there are going to be some kind of pain receptors that are going from here and going to the central nervous system. And there are also going to be pain receptors that are coming from around here that are going up to the central nervous system. And there happens to be this crosstalk that happens where there's pain messages coming from the heart, but then it kind of does this kind of crosstalk, and all of a sudden the brain is getting messages as if there were pain messages that were originating here at the arm, even though there wasn't any pain at the arm. But the brain doesn't know the difference. All it knows is that it's getting these messages. You know, again, we talked about that labeled line coding. It's getting messages that should be consistent with pain receptors being activated on my left arm. So this referred pain is saying there is pain that is actually coming from one place, but it's being referred to another place of my body. So even though the heart is the thing that's in pain, I feel like my arm's in pain. So this is actually a really useful diagnostic tool, because you can have pain in your back, but it might actually be coming like from your liver or your gallbladder. You can have pain in your, in fact, I can show you, let me come up with. Here. Ooh-ba-doo-doo-doo-doo. Here, I'll share screen, like something like this. You know, the heart is often going to be on your left shoulder and arm, which you can see here. You know, different organs here can manifest as pain on these different parts of your body. So it's useful to understand this, that this is a real thing and that it's used diagnostically. That pain that's actually not on your body, actually coming from organs, can feel like it's actually manifesting. It's being referred to the surface of your body. When we do this lab in person, we actually have people put their arms or their elbows in ice water. So we have somebody put their elbow in ice water, which is super cold. So that is painful. And after a little while, this person, I mean, obviously their elbow hurts because it's in the ice water, but the ulnar nerve, which is going under there, is also carrying all of the senses, like from the pinky of your hand and everything. Eventually, the whole side of your arm and hand start becoming cold and then painful, like your whole hand starts to ache, even though your hand is just in the air. There's nothing, there's no pain, nothing to cause pain in your hand. Instead, you get this kind of crosstalk at the median nerve here. Then your brain has this perception that your hand is really uncomfortable, but it's just this referred pain. You don't do that. Like, you know, in our lab, let me share what I put in the. So in this doing the general sensation lab part of the module, it says, do the 2-point discrimination, do the tactile localization, do the adaptation. You know, I said it all possible in case, you know, at this place, people aren't really sheltering in place alone. They now that we're all vaccinated. I originally made this when there were people that were literally like totally isolated. At this point, most people have at least somebody they can like touch. Adaptation of temperature receptors, do this at home. Referred pain, don't do the procedure. Here, all I wrote, it says, describe what you learned in this video and the clinical application. So I want you to watch this little thing here. This guy is going to talk about, you know, referred pain. And he'll describe it a little bit. I just want to make sure that in your lab notebook that you have actually slowed down enough to understand what it is and what the implications are. So for your lab, don't worry about actually doing the procedure. In fact, if you want to, you can, but you know, there's no reason to. In general, we try to minimize the gratuitous pain, making people experience unpleasant things. So And it says we will not be doing part 6. So that thing of touch local, density of receptors, don't worry about. So for this lab, I'm going to be done talking in another few minutes. Do part 1 in person with somebody who is game to do it with you. Part 2, part 3, part 4, and record your data. For the adaptation of, or for all the touch stuff, if you look, there's a little spreadsheet that's located in this doing the lab. It basically has the average 2-point discrimination and tactile localization and adaptation to the coins for a larger class. So you can compare your personal data to the larger data set to give it context and make sure that you're kind of consistent with the normal trends. So in your lab write-up, you will also want to include this larger class data to put your personal data into context. But yeah, I think, especially like right now, if you've got like over an hour that you were thinking you were just going to be glued to Zoom, this might be a perfect time to just like do this and knock it off so it's not just hanging over your head. Obviously it's going to depend on who's around you and your every other things in your life, but definitely don't just put this off. This is not something you can just do instantly. It takes a little while, a little preparation, and a little, so are there any questions about any of this sensory or general sensation lab? Yeah, it's too bad we're not doing it in person, because then we could just be together and have fun with it. But I still think you're going to have fun with it with whoever you choose to find as your subjects. And I really do think that if you haven't been thinking about the disconnect between what is actually in the world versus what you perceive, this is a great place to start to see that, just with like that touch localization. I remember the first time I ever did that, it was just kind of freaky. And the first time I did the thing, taking the two warm and cold adapted hands and put them in the same lukewarm water and wiggled my fingers around, it was freaky, in a good way. So yeah, I think it'll be fun to actually kind of get a better sense of how your senses work and adaptation and things like that.